Hello everyone. In this lecture we are going to discuss how to make graphene. Okay, so you can call it graphene manufacturing, you can call it fabrication, you can call it synthesis, you can call it production. That would depend upon what is the quantity that you're making. Are you making just one single layer or are you making a few grams of graphene? Okay, and it will also depend upon what is the pathway that you have selected for making graphene. Have you selected a vapor deposition technique, a chemical pathway? In that case you could use the term synthesis, or you are just peeling a layer of your graphite, highly oriented pyrolytic graphite material, for example. In that case you might want to call it fabrication, or you can use any term you'd like to use. One disclaimer, a very important one, is that graphene is single defect-free layer of sp2 carbon. That you know very well now from the nomenclature lecture, and I definitely recommend that you go through the lecture and also the references that I have provided there. So when I'm talking about graphene manufacturing, even though I call it graphene manufacturing, this does not mean that what you're going to get is only single layer graphene structures. Okay, what you are often going to get is a mixture of all sorts of graphene materials. So basically you may have some single layer graphene, but you may also have multi-layer graphene, you may have few layer graphene. In some regions you may even have turbostratic carbon, so more than 10 layers. So this is something that is important for you to know, that as on date we do not have any manufacturing process that would yield just single layer structures reproducibly. So here and there you can get a single layer, but that process may not be reproducible. So the second time you do it, then at that time you may not get the same shape and size of your graph. You may not even get single layers. Okay, so this is where we are at present. But the techniques that I'm going to discuss are they are for graphene related materials. The goal is to get graphene, but we may not always get graphene. And also remember that the properties, all the interesting properties of graphene that we hear about, the mechanical strength and the electrical properties, the electronic band gap structure, all of these things, they are valid only for single layers and not for the type of graphene we produce. Because these are multi and few layer structures, so all the properties cannot be translated. However, these materials also offer a reasonably high electrical conductivity, and that is why they are used in their bulk form in several devices. Now in the bulk form, again, whether or not you should call it graphene, well, judge it for yourself. Okay, so I'm going to discuss two main techniques. These are the two techniques which are very common. You can find various other techniques. You need to judge it again for yourself, whether they are bulk carbons or they are single layer graphene structures. But it is quite possible that we also have some other single layer fabrication technique which I have missed out. I know the two main techniques. One is the chemical vapor deposition. This is something that you're familiar with. This is nothing but pyrolysis of hydrocarbon that we used for making highly oriented pyrolytic graphite. So it is essentially the same process. In fact, I'd like you to also go through that lecture, because in the HOPG lecture, and also I think pyrolysis mechanism somewhere I must have described for methane. There we discussed the enthalpy of methane or any other hydrocarbon, how the enthalpy of formation changes with the temperature, and at which temperature then you have the optimum deposition, the solubility of carbon inside your metal. That is your optimum deposition temperature. So all of these things are valid also for this particular process. I'm not going to repeat them, so go through that lecture. Now we are going to discuss more details of the very process that is used, the reactor that is used for chemical vapor deposition of graphene, for example. Here we need to understand that in the case of graphite production, our goal was to get thicker layers because we wanted to ultimately anneal them out and convert them into graphite. But now when we make graphene, our goal is to get thinner layers, as thin as possible. If we could, we'd like to stop at one single layer, because that is our goal actually. So here the process slightly varies. We just need to ensure that the concentration of your reactant, for example, is in the optimum range, such that, and also the temperature and the pressure and all of the parameters, that is what we are going to discuss. Okay, in the case of vapor deposition techniques, there is also something known as physical vapor deposition that we will not discuss in detail in this particular course. As the name itself suggests, chemical deposition has some chemical reaction. But in the case of physical vapor deposition, you have the vapors, but you typically would evaporate a material from a certain target or a source. And then these evaporated molecules or atoms will be deposited onto another substrate. So that is a physical process. That's why you'll call it physical vapor deposition. And chemical reaction, so in our case pyrolysis is taking place, so there is a chemical reaction, right? So this is a CVD process. Now within CVD also there are a lot of variations. Again, we are not going to discuss all of them, but I have mentioned some of these names here because you will often find that, okay, graphene was prepared by plasma enhanced chemical vapor deposition. So what is plasma enhanced? As again the name itself suggests, you have a plasma, which, so it can be argon plasma and any other type of plasma, which is basically going to this is an ionized material, so that is the ions will actually transfer some energy to your sort of activation energy to your chemical process. And also the deposition process. Sometimes they will also improve the diffusion of these the species that have been formed, diffusion of these species into your catalyst. So basically you can perform the process at a lower temperature. So that is plasma enhanced CVD. You can perform CVD at low pressure or high pressure. High pressure in the context of CVD is atmospheric pressure. Okay, so you can perform the process at low pressure. That has also been reported for graphene manufacturing, and also atmospheric pressure has been used for making graphene. Okay. Then you can also, so you can have all of these variations and you can learn about them. There are various types of CVD processes, and again, that is beyond the scope of this course, so we will not be discussing them. Okay, fine. So this was the method number one. And the second one is exfoliation. What is exfoliation? Exfoliation means peeling something off. Okay, so from where can you peel a single layer of graphene? We have our highly oriented pyrolytic graphite. You can take a simple adhesive tape and remove one single layer, and then put that tape inside some sort of solvent, organic solvent. Then the the glue will dissolve and you will get the graphene. Okay, it's as simple as that. This method is not reproducible in the sense that, as I mentioned, again, you can get actually relatively large sheets of graphene by this method. You can also keep doing this tape thing again and again. You can get relatively large quantities as well, but you can imagine that this is not a very it's a reproducible method. Every time you'll get different shapes and sizes of graphene, and that's why although this people are doing this for certain device applications, this is not a method that is industrially used. Also, if you think of it in a fundamental sense, how did we get highly oriented pyrolytic graphite? We first performed chemical vapor deposition, which is the technique number one. We performed CVD or pyrolysis of hydrocarbon. We deposited this hydrocarbon, the carbon, which actually was in these graphene-like sheet or flat sheet-like structure, but it did contain certain defects. And also the structure, the arrangement was turbostratic. So we annealed it at higher temperatures. We performed hot pressing and so on to anneal out those defects and to give your material A-type crystal. Crystal arrangement. Okay, so now the sheets that you have in your highly oriented pyrolytic graphite, of course they are of very high quality. They contain very few defects. You also need to have the mosaic angle, which is less than 1 degree, and all of these things, right? So you got this nice graphite, and now from that graphite you're again peeling off one layer to go back to, in a way, your raw material, but annealed out raw material. If you'd like to use this process at an industrial scale, then that will be very expensive, because you see, you are performing purchasing one single HOPG sample and then performing the process on that. That is all right. That you can do for certain electronic applications. But if you want to ultimately make so many, if you want to make large quantities of graphene, this is not a feasible production method. So, but however, for a lot of device applications and so on, this is still extensively used. I will not be discussing too many details because actually I have already mentioned all the details. This is how it's done. Okay. Other methods, well, there are various methods that are that you can find in the literature. Many of them are actually producing are for the production of few layer graphene, multi-layer graphene. Some of them are even for the production of certain types of turbostratic carbons. So you know that if graphene is present in the bulk carbon, then you don't call it graphene. You can call it graphene layer, but even then you need to make sure that they do not contain defects and so on. So you can go through many papers. You can find it for yourself. Which method do you think is for graphene and which method is actually for turbostratic carbon? But here we are only going to discuss these first two. The first method actually is the second one I have already described. So let's talk about the CVD process, which is our method number 1. Okay. CVD, chemical vapor deposition, has certain chemical reactions. So every CVD process will have one primary chemical reaction in our case, that is the pyrolysis or thermochemical decomposition of a hydrocarbon gas. Methane is the precursor which is used most commonly. But again, this is not, we are not limited to methane. There have been various other precursors that have been tried out. Also, sometimes the liquid hydrocarbons such as certain light alcohols and so on can be sprayed and then decomposed, so they can also be used as precursors for depositing turbostratic carbon. Single layer or not, that is a separate question. Okay. What we often have is we have metal substrate as a catalytic substrate. Catalytic, let's say the collection is done on this, so catalytic collector of your graphene. Okay. We used just graphite when we were making pyrolytic graphite. We just used graphite itself as the collector. But now we use certain metals, often transition metals. Okay. If you remember, we were also talking about pore filling when we were, so this is a little bit of a different topic, but then we'll come back to the same point. When we were making needle coke structures, for example, needle coke to graphite, then we did the first carbonization step, and then we had a lot of pores in our structure. We filled resin or pitch inside those pores, and then we carbonized it again and then again and again to fill these pores. That pore filling can also be done using pyrolysis of hydrocarbon. So again, using the CVD process, what you can do is you can take that pore containing structure, put it inside your CVD reactor, and then you can deposit layers of pyrolytic carbon inside your pores. This process is very long, and of course it's relatively expensive, so it's only performed for rather high-end applications. For example, some very high-end composite materials, carbon-carbon composites. So in that case, you can perform this. So my point here is that you can perform CVD on carbon substrates as well. But in the case of graphene production, in order to obtain only single layers or few layers, and this is the minimizing the number of layers is the goal of the graphene CVD. So we often use certain metal catalysts, but again, a range of catalysts have been tried out. The most common ones are copper and nickel. Okay. Fine. So what happens inside a CVD reactor? So you can call it a CVD chamber, or you can call it a CVD reactor. There are various designs of these reactors. We'll be discussing some of them. Okay. What happens is there is a 4-step reaction. You know already. The first step is pyrolysis. So you feed your hydrocarbon gas inside the chamber. Often this hydrocarbon gas is then assisted or it is flown inside along with a carrier gas. Carrier gas is typically an inert or reducing gas which does not participate in the reaction, and it ensures that there is no oxidation taking place and so on. That's why often hydrogen is used, because this creates a reducing atmosphere. So you have this one inert or reducing gas. Along with that, you have your feed gas, and because you want to get only few or single layers, you don't want to have very high concentration of the feed gas, so you will have this carrier gas. Okay, and now once this entire mixture is inside your chamber, then the pyrolysis reaction takes place. You know that pyrolysis would only take place above a certain temperature. In the case of methane, definitely it has to be above 520 degrees, because again, that depends on the enthalpy of formation of methane. Okay, that is the step number 1. Then the second step is that whatever carbon, so after decomposition of methane, you get some carbon species. They are not necessarily individual carbon atom. So this we will discuss a little bit later. So these are carbon species that we get, which are currently present inside that vapor, or you can even call it a smoke, because if you have some solid carbon particles, you can call it a smoke. You have these carbon species. Now they have to somehow reach your substrate, and that is the step number 2, the transport of these carbon species to your substrate surface. Step number 3 is the migration on the surface of the substrate, and the fourth one is the film formation. So let me describe this with a picture. This is your heated substrate, and the thin yellow layer, let's say, is the catalyst metal layer. Okay. You have the gas phase reaction, that is your step number 1. So here you see methane, hydrogen. This hydrogen, the hydrogen is already present in your carrier gas. But you also may get some more hydrogen when methane decomposes, because that would decompose in carbon and hydrogen. So you'll also get more hydrogen. Okay, this particular reaction takes place close to the substrate in the case that your substrate is heated. So there are 2 types of CVD reactors. In one of them, the entire chamber is heated. In the other one, you only have the substrate heated. Mostly in the case of graphite production or graphene production, we'll use only heated substrate. So let's say in this case, only the substrate is heated. In that case, the gas phase reaction will only take place extremely close to the surface, where it has the high enough temperature for decomposition. Okay, so that is your step number 1. So you see there is this black particle I have made, that is carbon, but again that is a carbon species, not necessarily atomic carbon. Okay, now with this arrow I have shown the transport to the surface, or the adsorption of your carbon species on top of your metal substrate. So that is your this propagation and this adsorption, that is your step number 2. What happens after that is that these carbon species, now they migrate onto the substrate, and here temperature can make a big difference. So this is a very temperature dependent process, and it also depends upon the solubility of carbon in that particular metal. And that is why different metal catalysts actually provide different kinds of film thicknesses, for example, or the flake size even. Because the migration process or migration behavior of carbon species in different metals is different. That depends upon the solubility. That will also depend on the whether or not your metal contains any vacancies or defects, or it is just a very flat single crystal type substrate. Whether you have polycrystal, single crystal, that will also make a difference. So depending upon all of these factors, your species will now migrate onto the surface. So this is your step number 3. Finally, when the migrating carbon species will come in contact with each other, they will form larger structures, and you will have nucleation, island formation. So when a few carbon atoms they come together, then you will see a little spot there, which is dendrite-like often. So these are called islands, and then you will have these islands. So this is the nucleation of islands. And then they will grow, and at some point you will have a complete film formed. So this is basically film growth, film nucleation and growth process. So that is your 4th step. So this is already where you have this is the basic idea of your CVD process. Now one more thing is that in the case there are some byproducts being formed, then they need to be released as well. So they need to be desorbed from the surface. So that is also your sort of yet another step that you can add. In the case of carbon materials, you would say that it's the methane that is decomposing. So where do we have the byproducts? The mechanism, again, we'll describe a little bit later. It's not just methane decomposition. That is not the only thing that's happening when you perform the pyrolysis of methane. Actually, there are also other larger hydrocarbons that you can see. So sometimes these methane or the radicals that are formed after methane decomposition, they may combine with each other and end up making larger cyclic structures. And here and there, these cyclic structures may release hydrogen at a later stage. Not necessarily always in the gas phase, but sometimes also on the substrate. So it is possible that you do have some byproducts, and these byproducts need to go out. Of course, hydrogen can also be considered a byproduct in this particular case, because you don't want to have the film, you don't want to have any hydrogen in the film. In fact, you want as high purity of the film as possible. Okay, so Now, what will be the optimization parameters? So this was just the process, right? This is not the reactor. So of course, when we talk about the design of the reactor, a number of things become important. The temperature, of course, the substrate temperature is important. Okay, that is also determined by what kind of catalyst you're using and so on. Okay, that is number one. Pressure inside your chamber, because pressure, as you know, influences the diffusion process. Pressure influences also the flow patterns of your hot air inside your chamber. So the flow patterns, of course, also become important. The gas flow rates also influence these patterns. The residence time of your hydrocarbon, because that would also determine the film thickness. All of these factors, these are the factors that we are going to discuss in the next few slides. If you so I already mentioned that the pyrolysis of methane is something that you should definitely learn, because the very fundamental idea is that of the enthalpy of formation of various hydrocarbons, and accordingly you optimize your CVD process. Okay, so now we are going to discuss some various steps of this process. Okay, so what we are going to do here, we'll understand this process in we'll divide it into two parts, just for convenience. First one would be the reactor design. So reactor design, some of the designs or the basic ideas of the reactor that I will describe, they are valid also for other CVD reactions, so silicon CVD or metal oxide CVD and so on. So they are just like common parameters. But then we will talk also about specifically about the mechanism of carbon film formation. So let's see if we can, how much of that we can cover in today's lecture and how much will go into the next part of this lecture. But that's basically the idea. Okay, so let's first talk about the reactors. So CVD reaction takes place, and that is why you can call it a reactor, but you can also just call it a CVD chamber. People also call it CVD tubes. These chambers or reactors can come in different shapes. Often in the case of carbon material CVD, you will see tube-like reactors. Quartz tube, typically it's a quartz tube, but that's not necessary. Definitely different CVD reactions have different types of chambers. Okay. Importantly, there are two types of these reactors. One is known as the hot wall reactor and one is known as the cold wall reactor. So actually already in the previous lecture, we briefly talked about what happens if is your reaction taking place only in the gas phase, or it's also happening in the solid phase, or it's partially taking place in the gas phase, partially in the solid, and is there any effect of the solid? In the case of carbon materials, yes, something is definitely happening in the solid phase as well. Why do I say that? Because, well, different catalysts give you different types of graphene structures or other carbon nanomaterials. In fact, just by changing the catalyst, you can get a different carbon nanomaterial altogether. What does that mean? That means that catalyst or your solid support does have a strong influence on the process. So there is something to do with the deposition of metal, and then the solubility of that metal, and then the precipitation of that carbon structure. Definitely there is something there, and this mechanism is still being investigated. Okay. Well, coming back to the CVD reactors, we have two types. One is the hot wall and one is the cold wall. So hot wall, as we discussed previously, has the entire tube or entire chamber heated. That's why we say hot wall. Let's say TW is the temperature of our wall and TS is the temperature of the substrate. In that case, the first type, hot wall type reactors, will have TW almost equal to TS. So that is basically the idea. Your entire chamber is heated. In the second case, cold wall, as the name suggests, the walls are cold, only your substrate is heated. So in this particular case, your TS is much higher than that of the TW. Okay, so these are the two types of chambers. What do you think? What will be the pattern of reaction? Let's say you flow your hydrocarbon gas inside. What will happen? In the first case, it will, the reaction will take place everywhere. So you'll have this carbon smoke. It will not contain just carbon, but also methane, hydrogen, and some other species and so on. But you will have the reaction taking place in the entire chamber, because now your entire chamber is heated. Okay. You will then also, when the reaction takes place in the entire chamber, where does your deposition, where do you deposit the material? In this particular case, I have shown that there is a substrate, but you may also perform hot wall type reactions without a substrate. In that case, your material is deposited on the walls of your furnace or the chamber. Okay. So this is the first type of reaction. If you remember, in one of the lectures we talked about, I think it was carbon nanofiber lecture. I don't so you can see vapor grown carbon fiber. I think then I was talking about. We were talking about a floating catalyst and seeded catalyst methods. So basically, when you seed a catalyst, that means you have a substrate. Or you can also have the catalyst floating through your, inside your entire chamber. So the first type, the hot wall reactors, if you need a catalyst, if that support is very important, in that case, what you can have is you can have these floating catalyst particles. Often in that case, you will have particles and not a film inside your heated chamber, and then you can get the deposits on the walls of your furnace. Okay, so that is number one. And in the case of second one, of course, now here you have a substrate. So only this part is heated. So the reaction takes place rather close to your substrate in the heated region. And then the deposition takes place only on the substrate. Both of these processes have their advantages and disadvantages. Because also when it comes to the flow patterns of the gases inside, it becomes very important what is the type of your CVD chamber. Why am I saying that? So when you have a mixture of gases that are flowing inside, whether you should heat it or not, that is the question. If you have the heated gases, then you have the entire region heated and you don't have to worry about the heat, the thermal gradient inside your chamber. But in the second case, you need to worry about the thermal gradient, because now the air that is, or the gases that are close to your substrate, they will get heated up. Then they will have a different density, much lower density compared to the rest of the gases. Now you may actually end up getting some sort of turbulent flow. So one more very, very important parameter inside all the CVD chambers, you must have a laminar flow and not a turbulent flow, because you want to get a film deposition, right? Turbulent flow will, at some point you will have, at some location you will have a lot of deposition, then some locations will not have any deposition, and so on. So you definitely do not want a turbulent flow. So what you need to do is you need to have a laminar flow inside your system. Okay. Now there are also closed and open CVD chambers. But in the case of carbon materials, you will essentially have closed chambers. Open chambers, you can imagine, will enable oxygen to go inside. That would cause burning of our carbon species. So we always want to prevent whenever we are doing any carbon material manufacturing, we want to prevent the leakage of oxygen inside. So you'll typically have closed chambers in the case of carbon related materials. Yeah, so as I mentioned before, you must have a laminar flow, which basically means that your Reynolds number should be less than 2000. Okay, but you actually don't need to worry about it so much, because in most of the CVD reactors you will have Reynolds numbers of about 100. So 2000, you don't really need to worry about getting a turbulent flow. This can, however, only happen if there is convection, if because of these density gradient, because of the thermal gradient. So that is the only thing that you need to worry about. In principle, you will generally have a low Reynolds number. One thing, however, I must mention, sometimes what happens is you are trying to repeat a certain process. Let's say I performed a certain CVD process on one CVD reactor, and then tomorrow I'd like to now repeat it on another CVD reactor, and I'm not getting the same results. I'm not getting the same film thickness, so not getting reproducibility. That could be because the Reynolds number is slightly changed. So you need to always see what was the diameter of your previous tube and what is the diameter and length of your new tube. What are the flow rates and what are the parameters, even the temperature. Even when you change, for example, just your substrate, you may not be able to reproduce the same film thickness, because now the substrate temperature might have changed, and now there may be more thermal gradient inside your system. So Reynolds number you must always calculate for a particular system. Only then you can get the reproducible process. Whether or not it is turbulent, that is of course another thing. It must be laminar. Okay, so Yeah, CVD chambers also, of course, there are gas lines. There are many other things that I have not shown here in this picture. So these are just very basic drawings where I have only shown you the chamber. Now, of course, you will have various gas lines connected, and then you will have mass flow controllers. You will have various valves which you can open and close whenever you like. If you want to reduce the residence time or you want to increase the residence time, that all of these things are controllable. The concentration of your reactants is also controllable. So chamber, the CVD, this is not particularly, this is not the schematic of the entire CVD reactor that you can understand. Okay. The only issue is that you need to take care of this local density gradient. Because then you will have these convective lines because of the thermal gradient, and that is something which can create local regions of turbulence. And local regions of turbulence on top of your substrate are detrimental for your process, because then you will get non-uniform films. So this is something that you need to ensure. There is also something known as the boundary layer formation that we'll probably discuss now, I think, in the next lecture. Okay. Now, one thing that you can do to avoid these thermal gradients is to maintain low pressure, because that sort of reduces the probability of this kind of turbulence. Okay, then you can also what else can you do? You can also keep your gas flow relatively low. So that anyway velocity directly influences your Reynolds number. So you can also, at the lower flow rates of your gas, there is a lower probability of formation of having turbulent regions. So you can further reduce the pressure and flow rates in order to avoid these convective regions. Okay. So this is, we are going to discuss more details of the CVD process. However, we will be, since we are mainly talking about carbon related materials, it would be a good idea to also go through some other lectures available on NPTEL, which talk about CVD in general. So CVD of various materials. So that will give you a better understanding of how to work with the CVD reactor.